All right, so I'm going to go ahead and I started the recording right now. So most of this is probability, and then binomial theorem, all that stuff. But then the normal distribution stuff gets pretty heavily emphasized again on this exam. So if you did well in the first exam over that part, usually you do very well in this one. But if you didn't, this gives you another kind of shot at that. So this one is a kind of interesting one. I mean, it's just a wheel, and you're just trying to find the probability of certain things to happen. And remember, probability is a success. How many successes are there out of total? So it's like gets a 40% discount. So you can see it's just 2 out of 12. At least 40%. So that's going to be the 40s or the 100% discount. So there's 3 out of 12. So these aren't too crazy. Now, this fourth one here, the average discount per person. This is what we call the expected value. And I'm going to use my pen here. And if you've got your form, have you guys all seen the test 2 formula sheet as well? If not, go ahead and pull that up on Blackboard, the test 2 formula sheet. But it's got the expected value of a distribution is this fancy thing, sum the value times the probability of that thing happening, right? So this is how we find the average for a distribution, and this is not a uniform, right? It's not like they all have the same probability of happening. So what you do is you take the probability of events. So what's the probability that they get 10%? So 10%, right? Times what's the probability of that? Well, there's 1, 2, 3, 4, 5, 6. So really it's 1/2, right? Plus, and then the other thing would be a 20% times that's probability. So there's 1, 2, 3 of those. So that's what we can say 3 out of 12 or 1 out of 4, right? And then the last thing is 40%, and that was what, 1/6. So plus, I'm trying to cram it in here. So you kind of see the work right here. I guess I'm just kind of reiterating this work right here. So that's where all that comes from. The probability of that happening times the event. That's it. Add them up. So the average discount is 25%, is the average discount on a spin. So like if you're the store owner, you can kind of go, oh, so I'm essentially giving a 25% discount on average. Some people are going to get more, some people are going to get less, some people are going to get free shoes, right? So, or whatever they're selling in department stores. So, but I think that's, the expected value part, as I see some people miss that part. This last question here on number 1, I almost don't want to ask these questions because when I get wrong answers, I get sad. So it's like, so the person got 10% 5 times in a row, then they say, I'm due to get a bigger discount now, right? Well, probability hasn't changed. It's not like the last wheel. The wheel knows what the last history was, and all of a sudden it knows it's going to make it different, right? This is what we call the gambler's fallacy. Thinking like, well, my luck's going to change, or something else, something has changed with the probability because this other thing's been happening so much. What's funny though is it actually kind of is true, because we have this other thing called the law of large numbers, which means if I do things a lot of times, the more normal my experience should be, right? So when you go to a casino, on average you lose, right? Well, if I keep going, let's say I go and I win, but if I just keep going over the long haul, I eventually will lose, right? This is why they don't ever want you to leave once you go in. So, which tells me there has to be some highs and lows and ebbs and flows, right? But eventually it evens out to the theoretical model, right? And that's kind of like the law of large numbers. But then that leads humans who can't forget the last thing that happened, starting to think that that's actually going to change the next event happening. This is why humans cannot really pick random numbers, or they can't truly be unbiased, because we remember and we are biased, right? So if I told you all, hey, pick a number between 1 and 10, you all started chatting it in. As soon as Alexis puts in a 1, the next person is not going to say 1, right? Or they're going to say, well, there's copying them, right? But the probability of 1 is exactly the same as it was last time, right? So this is why humans are very bad at randomness. So there's my diatribe on all that. Any questions on this particular problem? Or should I just go to the next one? If you want, raise your hand. I can turn your speaker on if you want to say something, or if you have a question about something I said. Otherwise, I'll just keep going. In the solutions video, I go over all these problems, probably not to this level or that long of an explanation. So if you want to obviously watch that, I would. This is interesting. If you draw a Venn diagram of this, this is like when there's an overlap, right? And if you look at your formula sheet, it says probability of, let's call this, what's this? Stocks, and this is what? Brokerage firm and online. So we can just go B and O, right? So there's 50% are in this one, 30% are in this one, and 20% are in both, right? So it's the probability of A, here's the formula, plus the probability of B. But then you have to, if I take and say, if I shade this, like I shade this, right? I find this circle, and then I find this circle. I've added the middle part twice, which is why you have to subtract off the intersection, probably A intersect B. And then that works. So that's why it's 0.3 and point. So it's 80% minus the thing you've counted twice, which is the intersection. How's that? And these questions, like on this test, are going to be, pretty similar to what you'll have on this test coming up. You'll take by tomorrow. I like the one with the tables here are always good. The only thing, a lot of times the struggle is the A given B part, right? So if you just say, what's a randomly pick some, there's 175, right? This is how many they buy a warranty. There's all the people that buy a warranty, right? 175 out of 420, pretty straightforward. Warranty, buys a warranty or laptop. There's warranty and laptop. It's very similar to the one we just did up here. Probability of A plus the probability of B minus the intersection. So that's 175 and 348. But we've counted these 145 twice because they were in the row and the column. So that's the probability of getting that one or the other one. It's the same as number 2 here. And then what's the probability that a randomly selected consumer buys a big screen given they purchase a warranty? So this is where it gets a little tricky. And if you see the probability of A in this little thing is given B, if you look at your formula sheet, it's the probability of the intersection A intersect B divided by just the whatever comes second here. So this would be the probability of B. So this is a really short form of it, but if you want to, let's do a longer form. I'll make this blue again. So A intersect B. So how many of them big screen TV and a warranty, right? Big screen TV, 72, right? And a warranty, right? So how many were hit both of those things? That's 30. Now you could say, probably the A plus B, you could go a little more explicit, but the easiest is just find the intersection. You could divide it by the total, then the totals would cancel. And then the tricky part is only looking at whatever comes second, which is how many are in B. In this case, what's the second thing? Warranty. How many had warranty? 175. So you could do it like this, kind of like this, 30 out of 420 divided by 175 out of 420, which really ends up being 30 over 175. It's the same thing. So the way I'd like to teach this is just find the intersection. How many is that? And then only look at how many are in the second category. And so then that's why I kind of ask in the second one, what's probably of B given A? Same number on top, but now we're only going to look at the big screen TVs, which is 72. That's one that I see students miss sometimes. Excuse me. And this one's kind of interesting. Do you believe this that it do you believe the type of product affects the customer's willingness to pay extra? So what you're looking for is if they buy the warranty or don't buy the warranty, how does that compare based on what they bought, right? So that's 30 out of 72 bought the big screen, and 145 out of 348. Those are almost the exact same proportions, which tells me if they buy a warranty, it doesn't matter if it was a big screen TV or laptop. They're the same percentage of people buy it. So it doesn't seem like at least these two makes a difference because they're both probably worth about the same amount. I don't know. But if these percentages are different, then we'd say, yeah, there's something going on here. There, it does seem to affect, and we'll study more of that later in the course. But yeah, so if they're about the same percentage, we say it does not affect it. Or they're so you could say purchasing a warranty is kind of independent of what product it was. If it did matter, then it would say it's dependent on what product it was. So you can use that kind of language. All right. Questions on number 2. Am I taking too long or boring you? I know this is late, but is this what you were wanting, everybody? More explanation on each one of these problems? Okay. All right. 4 is accounting, right? So pretty much on 4, and then if you look in 5, the only real question you have to ask yourself on these is, does order matter? Okay. So if order does not matter, it's combinations. If order does matter, it's permutations. So again, here's the stats person in me that drives me bonkers. Does anybody ever have a locker and you put a padlock on it, or it has a lock on it? What do we call that? When your locker what? Let me chat it in there. You have to use your locker combination, right? Does the order of the numbers that you put in matter? So what should it be called? A locker permutation is really what it should be because order does matter, right? Anyway, I'm not going to change the world on that. So anyway, but that helps maybe helps you remember if order matters, it should be permutation. So the first one is I'm just picking 5 players out of 27. It doesn't matter who gets picked first, second. It's just they're on a team, or if it's like a committee, or if it's like a board, or whatever. If there's no ordering, or it doesn't matter what order things are, you can just use combinations. So 27 to choose from, choose 8, and there you go. And then what's the probability of getting, though? There's only one that would have the tallest players, right? So there's 1 out of 2,220,075. And then this next one is permutations, right? It says doing a lottery, 5 different numbers and 5 numbers in the same order, right? So wouldn't that be frustrating if you're playing the lottery and you've got all the numbers, but oops, you didn't have them in the right order? That would people would hate that, right? Which is why they don't make lotteries that way. But this is what this occasion is. So essentially, there's 20 numbers, choose 5. And then the second one is what if order does not matter? But look at the difference in the number of combinations. It goes from, what's that, 1.8 million down to 15,000 if order does not matter. But now you have enough information to kind of figure out like what's the Powerball, right? How many numbers are they picked from? How many are you picking? And then if they have like the Powerball, then you just times that number times that, how many combinations there are of that one. And then that's how you get I think, well, usually it's like, don't say 170 million combinations or something like that. It's typical for a lot of lotteries. So sometimes when the jackpot, like for instance, if you bought every combination and you won like $1 billion, but it only cost you like $200 million to buy every combination. Now, physically, you actually couldn't do it, but let's say you could. Well, why wouldn't you still do that? Well, a $1 billion jackpot is really only a $500 million jackpot because they take half of the money out for taxes. So now it's down to $500 million. Now, what happens if somebody else has the number 2 and you have to split the pot in half? Oops, now it's down to $250 million. Or if there's 2 other winners, right? So there's no sure thing in the lottery, even if you bought every combination. Yes, you would win, but you may not get the money you thought, which is why when it gets psycho big, everybody starts talking, well, now I'm going to buy it. It's like, well, your probability of winning is still the same. And if you're, it's like the worst slot machine on planet Earth. The probability of winning the Iowa lottery, in general, all the prizes, essentially they pay back 50 cents on the dollar. It's like a 50-50 raffle. So the percentage of payback is half. So yeah, this is one reason why it's actually illegal for you and I to have a lottery or to have a gambling facility, because you take advantage of people. It's essentially stealing money from them. The expected value of most casino games is like about a 10% house edge, 8 to 10% house edge. So every dollar somebody bets, casino's getting 10 cents. And they just keep doing that over and over and over and over and over and over and over, right? Oh, okay. Yeah. Do you have your TI 84? So hit math and then hit PRB, probability. You should see NCR and N. So this is, so if I wanted like this one, 20C5, you just type in 20 and then you hit your NCR button and then 5 and then enter. And that is what that would work on your TI-84. If you want a website that'll do it for you, Wolfram Alpha will work. That will, oh, that didn't spell right, sorry. Wolf, I'll try that again. Wolfram Alpha.com. There you go. So if you type that in and you put 20C5, it'll do it. So if you want to try that out. If you're interested in casino games, this is a really good website that shows you all the expected values. It's called wizardofodds.com. It gives you all the game calculations and everything. I'll put that in the chat too. Okay, let's see, back to that. There. Yeah, wizardofodds.com will give you all the different expected values, playing strategies, what's the expected value, what's the house edge. So essentially, here's what I tell people. Don't gamble. Or gambling's for, well, people who don't understand math very well. How's that? But then people go, have you ever gambled? I'm like, yes. So what game will I plan on losing money in? And the only game I've found of any worth is if you're at, let's say you go to Las Vegas and you're meeting somebody there and you're with your friends, or you're at a casino and you're like, this is stupid. Gambling is guaranteed loss over the long haul. Otherwise, I wouldn't do it, right? What I would suggest is you go and find the craps table and you put the minimum bet down on the pass line. The house edge on that is like 1.7%. So that means for every dollar you gamble, the house is getting under 2 cents. So you win and lose. So it's the slowest way to lose money. Let's put it that way. It's the slowest way. Plus, you get to watch a bunch of crazy people yelling and screaming, and you get to throw the dice every so often. So it's kind of a social thing. Don't be tempted to put your money on anything else besides the pass line. Everybody will try to talk you into it, but everything else out there has a higher house edge. So there you go. There's your advice if you have to go to a casino. Go to the craps table, play the pass line. That's something you can't do on the internet, right? That's an experience that you couldn't have people yelling around a table, right, on the internet. It doesn't work. So that I've done it a few times when at the math conference in Vegas and so forth. Actually, my family and I just went there 2 summers ago. We didn't even I didn't even gamble. Nope, my mom made me gamble $5 for her, which is just hilarious. So, but that was it. We never played. So, um, do I have any gamblers online? I know some of you are young, but I did one time have a professional gambler in my class. He was very good at Texas Hold'em poker, and that's why all the pros play Texas Hold'em, because you don't play the house, you play each other. And he was the smartest guy in the room, and he had a playing strategy, and he could make a living at it. So anyway, I asked him why he was in my class. He goes, "Well, I don't want to just click on a screen my whole life and take money from people." I'm like, "Okay, well, that's noble." Uh, there you go. Number 6 is almost identical to what we did on the last one with the expected value. What event? Probability. What's the event? Probability. Add them all up, there's the expected value, right? So this is where a car insurance company can say, you know, on average, here's how many we're going to have. Here's then the cost per claim, and then 250 days, how it's a total, and then what would we have to charge everybody for all these policy holders. So this is what insurance companies do, and this is what actuaries do. Actuaries would it's be more robust in this, but they would have functions that would model these very complex things. But really what they're doing is trying to find the average risk. They do a confidence interval. They take on how much risk they want to assume, and then they have to make sure they charge more, or else they lose money, which they don't want to sell products where they lose money, because no business can make it that way. But that's pretty much what is a very simplified version of kind of what an actuary does. What's the cost benefit analysis of, so like I have teenagers and they have to be insured. Well, almost no insurance companies would be able to insure teenagers because their average rate of cost is too high. But what they do is they spread the risk out by insuring their parents. So essentially, it's everybody's risk gets thrown in one big pool. There's some people who are high risk and low risk. So the low risk people pay for the high risk people. And that's the way insurance kind of works. But interesting is if you can get pools where everybody's low risk, then your rates go way down. Like, I'm getting old, so I'm probably getting the AARP group or something someday where like, oh, all these old people, don't get in accidents, or they're not going to charge as much. So this is where it always gets controversial, is how much risk is one allowed to defray or assume. And that's where it gets sticky. But insurance is just there because there's risk, and it spreads it out to more than just you. Like I have insurance on my home because if my house burns down, I don't have enough money set in the bank to replace it. So I insure that, and on average, every homeowner pays for the insurance of all the homes that actually do require claims and things. So, does anybody on this chat actually pay for their own insurance yet? Anybody got that going on? Yep, we got one. Nope. Yep. How fun is that, paying for insurance? It's lame. That's a good way to put it. It is lame. Oh man. But it's necessary, right? The liability if you hurt somebody or damage to your vehicle or all those things. So you're essentially you're paying for someone else to assume that risk for you. Yeah. And in fact, in Iowa, you can't even drive without it. You have to have insurance. So they don't. If you're going to drive, they want to make sure your ability to assume the risk that you're taking there. So, okay, let's go on here to number 7. So this is the binomial probability formula. I hope you all have that handy in your sheet. So this is NCR, P to the R, and then 1 minus P to the N minus R. So this is, and if it's binomial, it means there are only 2 options that can happen. So like flipping a coin, or in this case, it's a customer calling about that they get it resolved within an hour. So 40% of the time that happens, right? So what's the probability that out of the next 10, we get exactly 5 resolved? So again, how many different ways can it happen? That's the combinations part. This is the probability of the event here. This is the combinations part. This is how many different ways it could happen. This is the probability of that specific thing happening. And so you've gotten to practice that, and you do that a little bit on your discussion board for chapters, from chapter 5 there. And you can use the binomial calculator also in StatCrunch. Has anybody used that? Did you do that yet? Use the binomial calculator in StatCrunch? Give me a yes or a no, or a thumbs up or thumbs down on that, if you would, in the chat. Yep. Anybody else? All right, cool. So you can use that binomial calculator or the formula. I don't really care, but I give you, this formula to kind of show you what is it actually doing. And then B is what we call the complement, right? So what is the probability that at least one will be resolved within an hour? Now, to do that, you'd have to go with the probability of 1 or 2 or 3 or 4 or 5 or 6 or 7 or 8 or 9 or 10, and you have to add all those up. Now, that is a big pain. An easier way is say, okay, what's the probability of that thing not happening? And the way that would be is like nobody gets it resolved, and I just take 1 minus that. That means that would have to be all the other possibilities combined. So this is called the complement. 1 minus the probability of the opposite. That's called the complement. So that's a shortcut way to do that. Believe me, I've had some other people do it, like do all the calculations. You're like, oh boy, you could have done it really quickly. But C is very similar to what you do on your discussion board. Expected value, just N times P. How many occurrences? What's the probability of it? So on average, it'd be 4 customers would get it within an hour. And what's probably that all 10 would be resolved? So that's 10C10, 0.4 to the 10th, 0.6. That means nobody didn't get it done. And that's probably not going to happen. It's a small, it could happen, but it's like, what's Jim Carrey say in Dumb and Dumber? So you're telling me there's a chance, right? There's a chance, but it's probably not going to happen. All right. And I think, yeah, the last page is all the normal distribution stuff and the central limit theorem. So hopefully you feel comfortable with number 8. It's very similar to what we did in chapter 3. Find z-scores, look up your p-values. If it's the area between, you just subtract those. Same thing with 9, very similar to what we did in chapter 3. So it's like a review of what we did in chapter 3. So those usually people do very well on. And actually number 10 is pretty similar too. You just find the z-score, look up the p-value. And then, yeah, between, same kind of thing. Find your 2 p-values and find the difference. The tricky one is this part right here. So remember, in chapter 3, we only looked at the probability of a piece of data or one subject compared to the population or sample. The thing that changes here is we can start now looking at averages of groups. That's the central limit theorem. And if you did that animation, you notice that no matter what the host distribution was, if I find a group of like 10, I find that average, and I find another group of 10, I find that average, I find another group of 10, and if I keep doing that over and over, the distribution of those averages looks normal, which is why we can use the z-table, and this is called the central limit theorem. So that's the discovery you're supposed to make in chapter 6 discussion. So when you do that, so the only difference between, well, I'll do this one first. What score would be needed to be in the top 10%? You can either use your normal calculator in StatCrunch or get your z-table out and look for the top 10%, which is like the 90th percentile. And if you look that up, it's 1.28. That's how many standard deviations above normal the 90th percentile is. But you don't know the score, and you know the average, standard deviation, and you can solve this. And you actually had one of these on your first exam. So 85.24 is the 90th percentile, the cutoff for the 90th percentile on this one. Now this one's going to be asking what would be the mean of a group of 16 students would be that. So think of it this way. What's the probability? Let's say the average DMAC student makes $45,000 as a starting salary. What's the probability that I could find a student who makes over 60,000? Okay, you could do the same thing, right? 60,000 minus 45,000 divided by the standard deviation. So the standard deviation is 10,000, 1.5. Great. But now what if I said, what's the probability that the class average is over 60,000? Now that's a much more difficult thing to have happen because I've got like 25 people now. The average for 25 to be over 60,000 is much more difficult because the more we sample, the more normal our experience is, which then how do we account for that size of group? So the only thing we do now is right here. We just divide by the square root of n. That accounts for that. That lets us figure out how big the group is, and then that will then shrink the denominator, and then that will increase the z-score. So it's much more difficult for that to happen. So make sure you do the square root and the division first, and then take, like, this one's -5 over 2, and then look up that z-score. That's in your chapter 6 online homework. Hopefully you get several practices on it, but I just want to explain that a little bit more. And how about questions on this page? All right, any more questions on just finding z-scores? Pretty straightforward. Just use the z-score formula, use your table, or how many of you use the normal calculator on StatCrunch? You guys use that? I think there was a video on Blackboard for that. Okay, cool. Yeah, so just have that ready, use that thing, that'll be great. And it's kind of nice because you can even like put in the percentage, it'll find you the z-score, or vice versa, right? So it'll go both ways for you, which is really cool. And then it visualizes it for you, which is awesome. And that's all I've got for that test. And honestly, I'm telling you, the test you're going to take is very similar. So if I was you, obviously go through this test, go through the one before that, go through the one before that, practice them without any help, then go back and watch the solutions video. Do that a couple times, and you should do very well on your test. Is that acceptable, or do you guys want to go over more stuff, or anything you've seen on your reviews that you would like help with? Yeah, so somebody asked how many practice tests. Do a couple, and if you feel good about them, you're good. If you want to do more, do more. Another helpful thing is if you looked at my math lab, if you go to the course home, there's like a study plan. Sometimes it'll like identify certain problems you struggled with or you needed help with. A lot of times what I would suggest is when you're doing your online homework, maybe flag certain questions that you know were hard or they're similar to your review, or things that you struggled with. Go back on your online homework, and you can always redo those and have it not affect your score at all. You can do them for practice. It allows you that option. So you can do some of those, like for instance, the z-score ones like this in chapter 6. You can go just practice a bunch and see if you know what you're doing. It'll give you instant feedback. All right. So how about this week's discussion board? Do you want to talk about the chapter 6 discussion on the central limit theorem? Okay. So I'm going to go ahead and pull up that animate. I'm going to share my screen here. And share my screen. Entire screen. Share. Okay. Assuming you guys can all see that, is that correct? Put this over here. All right. Okay. And I'm going to go to course content. And I'm going to go into right here, week 4. And let's go to right here, the discussion. Okay. So if I click this applet button and I hit begin, is it not going to let me? Is it doing this? Hold on. Try this again. Here we go. Version of recording Java. Begin. Here we go. Okay, so now it starts with the normal distribution. You can pick like uniform, that's all the same, skewed, right? But I kind of tell you to do a custom, so you can actually draw your own whatever, right? So there's a multimodal weird distribution, right? It doesn't matter. It's whacked out. It even gives you the mean, median, standard deviation, and then these things called skewness and kurtosis, which we don't really study, but what you can do then is like animate pulling 5 pieces of data, right? And then it finds the average of those 5 and puts that right there. And I can do that again. And then it finds the average of those 5 and I do it again. Get the idea of what's going on here? It's randomly picking 5 pieces of data, and then it is finding the average of those 5 and plotting them, right? Now I'm just getting to 10,000 and boom. So even I've got this parent distribution that's really wacky, it's going to end up being a normal distribution as I keep doing that. So that makes it, that's the central limit theorem. The question is, and then it asks you to do it with sample size of 30, which I ask you to do that in discussion because that's not an option to pick here, right? And then if we do the same thing, right, I was at the 10,000 button. Okay, so notice the distribution is not as spread out. So the larger your sample, the more narrow or the lower your standard deviation, the lower the variation can become, because the larger the group, the more normal your experience. And if you use the formula, you can actually calculate it. It's like the formula we just used back there. It was sigma over the square root of n. So you've got S right here, 9.41. If I want to find the standard deviation of this one, it's 1.9. Well, I bet if I take 9.41 divided by the square root of 25, which is 5, that's how I get that. And so that's what I want you to discover and actually do on your one. So you're going to report your mean and standard deviation. You're going to do this animation. You're going to answer the questions. You're going to report exactly. So usually the biggest errors I see is people don't actually figure it out with the formula, what would be the standard deviation of that repeated means. And then the other error I get is people don't really define the central limit theorem in their own words very well. So I want you to kind of describe this idea of, you know, there's this, no matter what the parent thing is, if I do random samples, the distribution of the means of those samples becomes normal, something like that. So is that what you were, hold the chat. All right, is that what you're looking for, Catherine?
When I am doing my like own equation with the sigma over the like square root of n, I'm not getting the same standard deviation as what's showing on the computer.
Okay, so super close or not?
No, like even when I just did the 9.41 divided by square root of 25, I'm getting a really weird, like I got 1.882.
Okay, and that's pretty darn close, right? Because 1.882 is really, really close to 1.9.
Oh, so we're going off. Okay, never mind, because I was looking at the 9.41. So I
yeah,
guess that.
yeah. So it's kind of like, okay, what's the spread of the parent distribution, and what would be the spread of the repeated means? That's the central limit theorem would say, well, if I know the standard deviation of the parent, I can now find the standard deviation of these repeated means by just dividing by the square root of n.
Okay.
Yeah. So in yours will be using the square root of 30, right?
Yes.
Yeah, yeah, and that should come out, and that's so just kind of helping you discover all of these things. So this is what's so powerful about central limit theorem is, no matter what distribution we have, I mean, like, I don't know, this might be the distribution of I don't know, the days of sleep I get every in a month, right? Highs and lows. I don't know, it's all whacked out. But if I look at the repeated mean, the distribution of the repeated means, I can still use the normal distribution to analyze it this way, which is kind of cool. So now we can use this z-score thing and the normal distribution for about anything. Really, it applies. So yeah, that's your kind of first really powerful statistical theorem that works a lot. And then when we go on to like t-distribution and chi-squared and other thing, it just helps you understand, oh, there's different shapes of distributions. Why do those come out? And what are they measuring? And that's really good statistical thinking. So, cool. All right. How about other things for those in the 8-week class? Test review, chapter 6 discussion, online homework questions. Is there something that somebody would like to chat about? I'm going to hit stop sharing here. Get this other screen moved over here. I'm going to move it back. Some people have been reporting a few issues with Cam Scanner, which is kind of weird because you all kind of used that app already, in that first practice upload at the beginning of the course. So I'm like, well, usually if it worked then, it would work again. So yeah, so hopefully just give yourself enough time to, maybe email the file to yourself or whatever and upload it onto Blackboard. And I know we had somebody from the 16-week course, right? So for those in the 16-week course, you're finishing up chapter 3, discussion, online homework, and test. Well, actually they spread it out. So you were done chapter 3 last week. All you have to focus on this week is taking a test. And you 8-week people, don't be too jealous because they're going half the speed. So that's all I have to do is take the test this week. And I can't remember who was that. That is the 16-week. That was Maddie. Anybody else besides Maddie? Okay. So Maddie, how about you? Do you have something from your test review? Or I would really encourage you to look at the 2019 exam, especially the last problem, right? Just really review that well. And make sure you understand the z-score stuff on that. How to use your normal calculator or z-table. Which one do you usually use, Maddie, on that? Okay, you did that one today. Awesome. Good job. You're good to go then. I would love to say everybody's going to do that, but that's exactly what you should do, and you should be fine then. I guess one question I would ask is, and I remember the other students that are taking the test, what's the best type of sampling? You guys all remember this question? What's the best type of sampling? Yeah, random, very good. Why? Some people will say, oh, because it gives everybody an equal chance to be chosen. I'm like, well, yeah, but why do we? I mean, that defines what kind of random is, but why do we do it? And the idea is, oh man, good job. That's exactly right. Yes, reduce bias. Yeah. So we're stirring the pot, making sure that we have a sample that is most representative of the population's comfort. It's never perfect. It's never exact because the only way to get exact is to sample everybody and try to do a census. We're trying to do a census right now in the United States, which is hilarious. There's no such thing as you can't actually count everybody. It's called an attempted census. That's what we're trying to do as best we can. And I don't know, I'd be kind of curious to talk to somebody that actually works for the Census Bureau to kind of go, so how accurate do you think you actually are counting everybody? Is it 99.9? Is it 92% accurate? I don't know. Because, yeah, how many people are living in the United States at any moment in time? We don't know. So we tried, but we do the best we can, which is why I live in Grimes. We actually did a special census in 2015 because it was a growing community. So the count we had from 2010, from 2015, it didn't actually portray the number of people living here. So we did a special census so we could have an accurate count, and then coincidentally, then that's what the services you get and the money you get from the state or federal government is dependent upon those numbers. So it That's why growing communities will pay to have a special census done every 5 years instead. So that's why we did that in all right, how about anybody, other things that you would like me to address or questions? Yeah, make sure you get your discussions in. Anything you miss, you can redo. If you didn't attempt it before the due date, you get a half credit. But if you attempted your discussion and you didn't, whatever you didn't get it, you can keep redoing that till you get 100% if you at least started it before the deadline. All right. Well, again, I apologize. I was a few minutes late. Had just gotten back in the house from being gone, so I will stay on. But I'm going to stop the recording right now. But I'll stay on if anybody wants to ask, individual questions or whatever.